Okay, let us start. Our today's guest is Kurt Kremer. We are happy to have Kurt here for a few weeks. So people who want to consult with him, and I encourage people to consult with him because it's invaluable.
And free. Is it free?
No,
Nothing's free.
maybe not.
Okay.
Let's see who it is.
So Kurt comes to us from Max-Planck-Institut in Mainz, and to make the long introduction short, I should say that he is one of the major figures who is responsible for establishing computer simulation as the equal third part of soft matter science along with theory and experiment. So you should really carefully listen to what he has to say.
Thank you very much for this very kind introduction. So,
Is there a quiz?
what should I say now? Okay. Well, I would like to tell you a little bit about the problem of entanglements in polymer systems. So it has nothing to do with entanglements in quantum physics, where of course entanglements are also playing an important role. But I would like to convince you that entanglements in polymeric systems are interesting not only as a problem when it comes to rheology and things like this, but maybe we can even use something with them, or by avoiding them or by introducing them. And before I start with the details, I would like to mention the people who did the work, because otherwise one typically forgets this. Most of the work I'm talking about today is done by Xiaoping Su and Manyesh Singh. If I have time, I will also talk a little bit about work of Jan Smek and Stanard Pachong. Jan is probably still known to some of you as a former PhD student of Shura Grossberg, who then came as a very good postdoc to Mainz, and we had a lot of fun together. And then I will show some brilliant light scattering experiments performed by Georg Fütters and his group. And over the years, many other people were involved in different aspects. And of course, I can only give you a small glimpse of what we're working on over the last years. So, however, the first question, I think, because this is a general physics colloquium, one might address is, why the hell is a theoretical physicist, and by training, I'm a theoretical physicist. Some people might not remember this when I talk about these more chemistry-related things, but by training, I'm a theoretical physicist. And the question is, why the hell is somebody coming from theoretical physics interested in this plethora of systems? No? So you have a polycarbonate as a standard commodity, glasses, car lamps, and all these things are made of polycarbonate. Intrinsically, it's ordered protein, a protein in an elastic network model with only the active center given with all atoms. That's a essentially a polyelectrolyte with water and ions, kind of membrane structure, the sponge phase, and a typical block of a simple model of a polymer system. And if you think of it from a theoretical physics point of view, these systems are so different and so complex, it's very difficult to get a general structure on them to do something which you can call theoretical physics. No? Because in general, when you are a physicist, everything should be kind of generic and be in a general structure. And when you talk to a chemist and biologist, everything is specific. And somewhere there in between we are living. So these systems are much less well characterized than typically crystals in standard solid state physics. The chains have strong conformational fluctuations that are very difficult to grasp theoretically and experimentally. And that means that entropy is as important as energy. And the energy, the thermal energy at room temperature is pretty small. That's not a big energy when you think of electronic excitations or so. And of course, one has by far too many different systems and questions in order to arrive at a rather general theory. And in addition, when it comes to experiments, which in the end might be even an advantage, one has a very slow dynamics and long-time experiments are needed and so on. And that is something which typically, from a physics point of view, is not very effective unless one has some very specific questions. So here again is KT. That's about, at room temperature, about 4 × 10⁻21 joule. And if it comes to a chemical bond, the typical carbon-carbon bond is 80 kT. And that means it lives essentially forever. E to the minus 80 is infinity on our times and length scales. While the hydrogen bond, depending on polarizability and environment and so on, is somewhere between 4 and 10 kT. And when you take the typical energy, activation energy, e to the minus, energy with local frequencies and make an estimate, that makes a lot of sense in biological systems. And there are times which come out which are relevant in the biological context. So it makes a lot of sense that hydrogen bonds play a huge role there in many different contexts and situations. And if you want to get an overview, take your choice of KT, depending on whom you talk to. Everybody gives, of course, his or her specific measure. So in electronic structure calculations and so on, KT is about 2.5 times 10 to the minus eV, so 25 milli-electron volt, 10 E Hartree, 10 times 10 to the minus 4 E Hartree. That's what I like. In biophysics, 4.1 piconewton nanometers, so a classical force times distance unit, and so on. And of course, when you read papers from different disciplines join, one has to be very careful that people use one scale or at least convert it properly. Otherwise, you can get
Why
surprised.
not one? Why not just take KT equal 1?
Yes, as long as you do a simulation, for me it's KT equals 1 in most cases. But when I talk to my friends from chemistry to do an experiment for us,
Right,
then they get you down to earth
right.
and tell you what you have to take into account. So, but when that was the situation many years ago. But when at the time when statistical physics in the context of critical phenomena was a very hot topic, De Gennes had an extremely interesting and good idea. And I don't know, maybe you know, Shura, whether this was an accident that he got this idea or whether he had the kind of idea in the back already, I don't know. But the point is the following. If you look at the typical spin systems, and in the 70s with renormalization group theory coming up and so on, these were the prototype systems for statistical physics to check universality, scaling concept, and so on and so on. And when you have such a system and write down the Hamiltonian here, you can have an Ising model or an XY model. You can do a high temperature expansion, for instance, to get the susceptibility. So you have to make a high temperature expansion for the correlation function of this spin with this spin. And that's essentially the sum of all walks from here to this point. There is a coupling constant to the power n, the number of steps, and then the number of steps, the number of walks with this many steps. And here are just two examples of walks with 10 steps between 1 and r. And Van de Gennes made a very interesting kind of proposal. He said, well, if I simply take the formal limit that the number of spin components n, which is 1 for Ising, 2 for xy, and then you have Potts models and all these kinds of models, formally goes to 0. When I do this, what I find is that only self-avoiding walks remain. What does that mean? That means that, for instance, in this case, this red walk here gets weight 0, so it doesn't count anymore, it doesn't exist, so to speak, and only the blue one survives. And that means in this limit n to 0, only self-avoiding walks survive. And this is in so far extremely important, as that means that any lattice, as long as it's 3 dimensions, or whether it's a continuous space, has the same critical properties. And also has the same critical properties for this n to 0 limit, and that means that only self-avoiding walks survive, namely walks where, if I take a polymer now, the two monomers cannot sit on top of each other anymore. And by this, De Gennes proved, so to speak, that, for instance, the typical end-to-end distance squared, so the expansion of a chain, can be given as a prefactor A times the chain length, number of steps, to the 2 nu, and this nu is universal. That's the famous Flory equation for the exponent nu. The best value in 3 dimensions now is 0.588 something. And all the chemistry is hidden in this A. And needless to say that this is at least as complex as this. But for a general physics point of view, you can solve many problems when you look at this exponent nu. And you can actually have a direct correspondence between the inverse chain length. This corresponds to the normalized distance from a critical point in the weight of chains which count for the susceptibility. So that means a single chain for n going to infinity corresponds to an n to 0, small n to 0 limit magnet at Tc. And that was very important because it allowed to measure critical exponents, general critical exponents with polymer systems, and that was a big industry. In the early 90s, late 80s, that was a big industry, especially in Newton scale. So that means that this polycarbonate and this intrinsic disordered protein in solution, for instance, essentially behave the same. There's a prefactor in between, but all the rest is the same.
Sorry, I'm not from this field. And so if you don't have magnetization, what's the macroscopic quantity that you measure in a phase transition? Like I would say all the spins go up.
First,
so-
where you measure, for instance, the magnetization. When you have a magnet
Yes, in this
and
case,
cool
when
it
I
down,
see-
you measure the magnetization. You can measure the susceptibility, and the susceptibility goes with T minus Tc to a critical exponent.
Yes.
And you have an equivalent critical exponent for polymer systems. And in many cases, that was simpler to measure than for a magnet.
But what is the
order
what's the
parameter,
polymer?
that's
Yeah,
what's
what's
the
the
order
yeah, exactly? Yeah, thank you. Yes.
The order parameter, if you write it down with finite concentration, is the concentration of chains. Okay, so that means that these two chains essentially behave very similar. And that means when I take all these different systems, disordered protein, DNA, cellulose, polylactic acid, polyethylene, and so on, eventually they all follow the same behavior for the typical extension of the chain, which is a measure of the correlation function which makes for susceptibility. And again, this is universal. Sorry, that's L now, it should be N. And this is the chemistry. And then together with that, that was the time, not only the N2 theory came up, but also there was a lot of theory about disordered systems, Edwards-Anderson, spin glasses, and so on, the relation with Edwards went on to gels and networks and so on. It was the time of beginning of powerful Monte Carlo simulations for simple spin systems, Ising models and so on. And then also neutron scattering then developed rapidly. Here are just a few names, Fischer in Mainz, Springer in Jülich, Benoit in Strasbourg, and in Stein and Amherst, and many others. And that led to a kind of paradigm change, namely from using physics to study some specific applied polymer problems to using polymers to study general physics problems. And that made the field really exploding, and at many places in the world, people in physics started to work on polymeric systems. And I don't know whether it was accidentally, but it also was kind of a time when our institute in Mainz was founded. So this is the situation where I'm living now in scientifically for the last 30 years, or almost 30 years. On one hand you have a chemistry, on one hand you have a physics, and when they meet and try to interact, it becomes interesting and with many interesting discussions and friendly minds. And in this context then also we can ask this question and know that this problem is essentially the same for all kinds of systems. Whether I look at a biopolymer or whether I look at a single commodity or so, this is a very basic problem which applies in a very similar way to all these different systems. Namely that this is something fundamentally different than this. We know the carbon-carbon bond is ATKT, so this will never happen under normal circumstances. And when I now have a linear polymer and have this situation and this situation, if these chains are long enough here in both directions, and I can use this A to kind of manipulate the dynamics, I have essentially the same situation as here, that this is for living essentially forever, at least on reasonable timescales. And this is a big problem on the one hand, but on the other hand, I can also use that to do interesting things and to make interesting things. Here's an example from biology that is not a DNA. An electron micrograph, you see that this structure here will never go back to this one unless you really cut through the DNA. And then I map this onto a linear chain that is this situation with very long pieces of chain at the end. And there's a list of knots in papers by Meran Kadar and others, where you see the following interesting aspect. So you have this knot here, and when you let it fluctuate, and the conformational entropy of all the rest takes care that this knot is pulled tight. There's a very characteristic phenomenon that the entropy, I said in the beginning, that entropy is as important as energy in the system, that the entropy here really tightens the knot in order to allow the system to have enough conformational freedom of the overall chains. Here's another example, work of, in that case, of Tobiana and Podestillo, where they took such a chain and pulled slightly at these chains, and you see that this knot is locally localized. It can move up and down the chain, but it stays very tight. And there are some ideas that this might have something to do with Frenkel-Kontorova concept and so on, but I don't want to go into the details. details here. I will use that picture later on in a completely different context again. And here's an interesting table, if you like it. You can find many tables about biologically motivated knots, and they can become much more complicated than the few words which I'm trying here. So, but what I'm interested in here is more systems with many chains, and this is a very old graphic from the PhD thesis actually of Ralph Everest. Some of you know Ralph Everest. So what we looked at a diamond lattice network, so a network where the cross-linking points which connected the chains had a diamond lattice structure, and then you can fill it up with many such networks to have a melt density that then you can pull at this system. And then you see, because all chemical paths from here to here have the same length, that there are, due to knots, topological paths which are shorter. And when you then pull at the system, you see that here such a topological path, which is the shortest path in the system, essentially carries all the load. So the classical rubber elasticity, I don't want to go into the details here, but where all the chains contribute in the same way, and such a disordered system doesn't hold. Essentially all the load is taken by these two sets of strands, and that is defined by the topologically shortest path through the whole system compared to the chemically shortest path through the whole system. So what we are now looking at is a situation like this. Not single chains, we look in situations here where you have many, in that case, snakes or many spaghetti or so, and how do they behave under certain constraints, and can I do something with them to make something interesting? The first important point is that the standard binary picture gets into difficulty. So this is a simulation block of 1,000 chains of 2,000 beats each, and the details are not that interesting. And here, in many cases, you have a situation like this. No? There are 3 chains in a cartoon like this, and they are like these Borromean rings. If you close this one here, if you close this one here, if you close this one here. And these Borromean rings have the interesting property that if you take one ring away, the other 2s are not linked anymore. So it's a real 2-3 chain system, which you cannot resolve by 2-body interactions very easily. And this is, of course, something which is not new, so it's known already for many hundreds of years. So that is from 1540. Here you see the signature of the church, door of a church. You see the signature here for the Holy Trinity in this Italian church, or a different kind of Holy Trinity in this Irish beer. But that you have really this multi-chain effects certainly are very important and cannot be ignored. The way to deal with that actually goes back to Dejean and Edwards, or Edwards and Dejean, I should say, because Edwards already in '67 realized if I have a polymeric network, so it's a system of many chains with cross-linking in between, so that they are connected to each other, that this middle chain only can fluctuate around a kind of tube-like region along its own backbone. Because any leakage here would cause huge entropy penalty of the order of half of this kT times half of the strength of this loop length here. And this is because, of course, chains cannot cut through each other. And then a few years later, Dejean realized if I have such a situation like here, and then move this point way out here, and move this point way out here, then this middle monomers here on all reasonable time and length scales do not know whether they are in a network or in a melt. And as a consequence, he could explain why polymeric melts and no polymeric networks behave on large range of time and length scales identical. And only for very long times they start to differ, that the chains can diffuse and the networks cannot relax. And that led to characteristic quantities which are again chemistry dependent, but within these properties, when everything for all different polymers essentially is the same. So you have a characteristic tube diameter here of this tube-like regime that leads to an elastic plateau modulus, which is not of interest here so much, and you have a characteristic relaxation time within that diameter of a tube diameter, which is called tau relaxation time of an entanglement length, and that is proportional to this contour length in this circle to the power 2. And once I have these numbers, I can plug it in for all different polymers, and I can really quantitatively predict properties of commodities and also of biosystems. And that this picture works, you can see here from a direct observation of entangled DNA. So this DNA is fluorescently marked, and you see it at 2 different times, and you see that it moves up and down, and especially that it can only resolve new space, so to speak, from the chain ends. Where the chains go out of a tube, it can pull back and go in a different direction. You can, for DNA, you can directly observe this, and this also explains, for instance, the typical viscosity behavior. Only look at this picture. What you have here is the melt viscosity here versus the molecular weight of the chains in the melt, and you have a short chain behavior. So the chains are so short that they fit as a coil in this tube-like regime, and long chain behavior, and you see they all behave the same with some shift, which is chemistry dependent. And of course, this chemistry dependent shift can determine whether your extruder blows up or not, but this is a different issue. So the question still is, can we understand this better, and how can we get a hold on this also from a numerical or simulation point of view? What I have in such a melt is I have a situation that the chains overlap strongly. In a melt, the chains behave like random walks, so the typical end-to-end distance squared of such a chain is proportional to the contour length. The distribution of the ends is a Gaussian, and that leads to a self-density which goes like n to the minus 1/2. So that means the volume of one chain is shared also by n to the 1/2 other chains. And these n to the 1/2 other chains have to impose order of n constraints here on this red chain, because otherwise it would not be in the tube. No? If the density of constraints would go down with chain length, you would not have this tube kind of behavior. There were many attempts to do.
Can you explain that? Is that related to the entropy argument of why they don't come out of why they reptate within the tube?
So if the hole, so to speak, you would get out to make this loop, would become larger and larger, the entropy penalty would become smaller and smaller to do that.
Mm-hmm.
And if the number of constraints along the tube would not be in average a constant, that would mean with increasing chain length, the penalty would become smaller. And that would mean that this simple reptation type of picture could not work.
I see.
Okay, so so there are many attempts to do this. For instance, one way is to use Gaussian linking numbers between hypothetically connected chains, closed chains. But then what you find is that the average linking number squared, because this is 0 plus minus 1 plus minus 2, is proportional to n to the 1/2. And that means that n to the 1/2 times w to the squared to the 1/2 only gives n to the 3/4. That means this simple argument does not work. The binary contacts are not enough, so these many chain contacts play a role. There were many attempts to improve this. There's famous work by Iwata and Edwards years ago where they looked at the local approximations to the Gaussians and then took the absolute values to sum it up. But in the end, they were not able to really, they admitted that they were not able to really get a hold of a real number for how to calculate, for instance, the entanglements. So what we're now doing is we're trying to look at this from a completely different point of view, namely from a bead spring model simulation point of view. And our chains look like this, and they look like this in a way that these springs are very stiff. We have the data if you're interested. So that any crossing in our case is about 70 kT. That's on the computer, that's as 80 kT, that's enough. We never will cross 70 kT. And now we can look at such melts, and this is here a typical block of a polymer chain with different stiffness. If somebody is interested, I can explain this in more detail, but we are able to properly equilibrate such systems, and that gives then plateau moduli as expected and so on. When I do this, then you see how the chains move around, and this is just an example of a chain of about 30 entanglement lengths, and you see that essentially this middle part stays in the tube. But it also shows that this view of a rigid tube, a metal-like tube or so, is of course oversimplified. No? That's again a kind of average picture in a simplified picture. But you see that this chain remains in the tube. So I think the equilibrium properties are reasonably well understood. Of course, there's a lot going on in rheology conferences about details, processing, and so on and so on. But I think that is not what we are really looking at now. Question is, can we do something with the entanglements to make something new? Either to use them to structure materials or maybe to avoid them, to get very long chain systems with very low viscosity, which might be also of interest in many cases. So what is the situation we have, or what we would like to use? So you can, if you take a typical cartoon of a non-equilibrium situation, here we have a kind of very simplified free energy landscape and a reaction coordinate. So you can be somewhere in a local minimum. Typically, all soft matter systems which are of practical interest are not really in thermodynamic equilibrium. They are somewhere stuck in the processing. So you are either sitting here and the barrier is too high in order to approach the global minimum. That is a typical barrier, for instance, when it comes to cutting of chains or so. But what you have in most cases is something like this. You have a very rough free energy landscape coming from the local interactions, which produces the local friction of the beads. And the system can progress along this rough path. And now you can change the temperature, and then you have suddenly this situation, and then your system is stuck where you are. So you can use this really experimentally or in simulations to do that, and you can use this especially because of the Vogel-Fulcher type of behavior, which polymers typically have. So this is a very famous Vogel-Fulcher-Taman plot, or Kohlrausch-Williams-Watts from Austin Angel, also called Angel plot. Some of you might have seen it. And what you have here is viscosity versus the inverse temperature, so Tg, the glass transition temperature, divided by temperature. When you have a so-called strong glass former like silicas, it's essentially a straight line, which means it's a Arrhenius type of behavior. And if you have a fragile glass former, it goes like this. So it becomes liquid over a large region, and when close to Gg, the viscosity increases dramatically. That is a typical polymer behavior. And the simulation model we typically use has this type of behavior. You have a glass transition temperature here, and you measure the viscosity in the simulation. At high temperatures, you have a more or less constant value and Arrhenius type of behavior. And then you have this dramatic increase. And that means that in order to play around with these materials, and this is actually technically used in any die-cast process in technology, that if you are above the glass transition temperature, if you have the right material, you only have to heat it up a little bit above 2G and it becomes very liquid. And if you would have a typical strong glass former like a typical glass here, like window glass or so, you have to go to much higher temperatures. So this is a technologically very important aspect. So now, having said that, and that we have such a model, we can try to see what happens if I want to use that to do something with this material. So this is our block, and now we expand this block. And we do this in the following way. So these are some numbers for the systems, but this is more important, that our elongation ratio on the one hand is very slow compared to the relaxation on that scale here, on this tube diameter, so that I do not impose overstretching locally, but much faster compared to the overall relaxation of a chain in the tube. And when I do this and do such an expansion, I start out with a system expanded, in that case by a factor of 5. It's an isochoric expansion, and let it relax and ask myself what happens upon this relaxation here. In principle, you expect that the chains pull back into the tubes and kind of reorganize as Gaussian objects. And this is, of course, the ultimate state I would like to reach. So this is how the process looks like. You start out here, but then you extend it, and what you have here, the green one, is the original path of a chain, and the red one is the so-called primitive path, so the backbone of this tube-like regime as it was explained by Dejean. And here you see what happens when it relaxes over time. And this is what we would like to understand better. So what one would expect, as I said here, that the chain pulls back in here and then explores new spaces. And to do this, we look at this primitive path analysis. I think I don't want to go through details here for the sake of time. And what you find is when you calculate the primitive path along the backbone of the original path, you see that when you count kinks here, local kinks in this primitive path, but you have many kinks, and that each kink is essentially an encounter when two chains come like this. And now when you pull at this system, you see that the number of kinks becomes much smaller and they become sharper, which is kind of understandable, because if I pull in a certain direction, I might have even either straightening out or making it sharper, depending on how this kink is in space before I expand it. And so this is not so surprising. It's already very significant, at least when you see that this extends here over 300 monomers, 200 to 300 monomers. But what is interesting now is when I wait for some time. So I take this original state, and then I wait for some time, and then I see that the number of kinks reduces dramatically, and I have large straight lines where essentially I do not have any kink in my primitive path. And when I look at the time here, there is a time where the chain only has explored a little bit of the chain end. So essentially they stay in the tube. So to a first approximation, the number of topological constraints has not changed between these two states. So something must have been going on with the connections of the kinks between the chains, the knotting of the chains. And so that is the number of kinks. You can count them and measure them. And what we find is when we look into this more carefully is, so we start out with this situation, then we do this elongation, and essentially we have something like this in a very simplified cartoon, and then we let it relax, and then we get essentially something like this. So it looks like that in this process, the entropy, the conformational entropy of the chains pulls these knots or these links tight, and that increases the friction, this A factor, in the beginning of everything, which makes it even slower, even though we are way above the glass transition temperature. And this reminds very much of this situation here again, because again, we have a system which is under tension, and we have knots between the chains, and it looks like that we get a very similar situation as in this single chain simulation. And you can then, we can analyze this. You see here kind of congestions of close links between different chains, which then survive for a very long time. That's for extension of a factor of 5, that's a factor of 10, and you see similar pictures.
There's an Italian saying, which is tutti nodi vengono al pettine, which means all knots come to the comb, which is this.
But I think the Italians
Come to the comb. So when you comb your hair,
Come
eventually
to the comb.
you meet all the
yeah,
knots.
it's a little bit a simplified picture when you take such a totally disordered system, take two combs and pull apart, and the knots aggregate.
Exactly.
Yeah, that's. It looks like a molecular system which it's very close to that kind of picture. And you can go on. You can say, of course, what happens if I now have an expansion in 2 directions, but then the interesting thing is not so much to have a system with periodic boundary conditions so that one has fully bulk. So what we're doing is we're doing that for a freestanding film. So again, with the same way of making, preparing these equilibrium melts by also using universality by starting from Gaussian blobs and step by step introducing more details. Xiaoping was able also to make perfectly equilibrated freestanding films of different thickness. And then we take this system, again of long chains, 1,000 chains of 2,000 beads, which gives 70 entanglement lengths, so that corresponds to 1 million molecular weight in polystyrene or PMA. And then we expand this in the same way that locally everything can relax on the tube diameter, but globally the chains essentially have to follow the deformation. And that is what happens, and the few chains are shown, the rest is not shown. Then you see that many holes form. And of course, what you would expect for a standard material, you would expect that these holes grow and coagulate, so that you have one big hole, because that would minimize the surface tension. But here it looks like that they are stable, and they are stable because here the chains, and these are just 6 chains, 6 chains shown, because the chains are so long that they expand over many different holes. And we can look at this in more detail. So we start with this, that was the last picture you saw before, and then we let them relax, and you see that essentially nothing happens. The holes become a little bit longer, but the chains remain essentially where they are, and especially here at these points where many chains come together, the local friction becomes so large that essentially the system is stuck, and that nothing happens.
But there's nothing there, right? They could go in the way.
If I could go away, that's empty. That's empty space. So in the simulation it's vacuum, and in the experiment it's air. And then we can look at the conformation. So this is just one example, the original chain in this box, and then we expand it to 4 by 4. I think it's not a perfect square, the way I did it by hand. Yeah, to 4 by 4, and then you see this chain blown up as the primitive path of that chain with the connections of all the other chains where they produce a small kink. No? And now you can take this very chain and compare this to the same chain under real expansion and see how this looks like here. And you see already directly by eye that essentially the conformations are the same. There are only very little changes here at the very ends, but in principle here all these all the conformations and the details remain the same. And you can also take that and cool it down, like this here, towards the glass transition temperature, and then you get a stable, rock-solid, nanoporous film. So this is of course something where one asks, that should be possible to be made by experiment as well. When you make nanoporous polymer films in experiments, it's complicated chemistry, people use solvents and all kinds of things. But this would be just a dry sample, just a piece of plastic, and deform it. And we said, okay, maybe we try this, and it was done by Manjesh Singh, and actually the students of my experimental colleagues were very surprised when they saw me in the lab at some stage, but I left them pretty fast. So we took a film of polystyrene, glued them to a tube, heated them to above 100 degrees above the glass transition temperature, and then immersed them into vacuum so that we have this expansion here. And when you do this, and here I have all the collaborators who help with X-ray scattering, electron microscopy, and what you see is you get these little heads, and when you take such a piece of a head out and make an electron micrograph, you see typical nanoporous structure. That's not absolutely isotropic, but that is also because of the way this pulling works. And now you can take the diameter here. So we know that if we map the tube diameter of polystyrene onto our model system, then the tube diameter of the model system is 5 sigma Lennard-Jones units. Polystyrene is 5 nanometers. So 1 sigma corresponds to 1 nanometer. And that means we have here about 30 to 50 sigma. And here, when you take the scale bar here, we have about 50 plus minus 20 nanometers. So that is almost quantitative. It's surprisingly good. And so what we did is we took this system and we threw it into liquid nitrogen. I think we could have kept it also in air. This is stable for months on the shelf. It's a stable nanoporous film made just from dry polystyrene. Here's again the situation in the
I
comparison.
don't understand. You put it in liquid nitrogen,
To cool it down very fast.
but then you said it's stable on the shelf. You have a shelf in liquid nitrogen?
No, put it in and then take it out and put it on the shelf.
Ah, okay.
No, I don't have liquid nitrogen in my office. So here's this comparison again. So with 5 nanometers and 5 sigma, as I explained before. When you
But
take,
if you cool it very fast, what does it help you?
we cooled it very fast, but when you take the typical Vogel-Fulcher type of behavior and do the analysis, just putting it into outside air would have been enough. Because it's so slow.
Well, I mean, if you cool it fast and then you leave it there, then imagine that you quench rapidly and all the disorder remains there.
Yeah, but
But
this is.
if you then put it back on the shelf, you just go back to where you were, right?
No, but this is what was put.
No, I understand, but what I'm saying is that the fact that it's stable on the shelf, it means you didn't need to put it in liquid nitrogen,
Yes.
right?
So if you wanted to do a negative control experiment and you wanted to take a polymer and not have it do that, would you just have like shorter chains?
If the chains are too short, you will get one big hole.
So there's like a threshold,
Yes.
both density and chain length.
And
at
you
which-
need that this is a glassy state. I will come to that in a second.
And nothing else special?
Yeah.
No adhesive
nothing,
links,
No,
no
nothing.
loopiness?
It's a standard
It's like
polymer melt and nothing else.
Okay, thanks.
So, and I don't want to show all the scattering experiments, but I would like to show us the brilliant scattering experiments by Georges Freitas, So what you find is you find the change in the moduli, depending on porosity or expansion. 0.4 is in porosity is the largest expansion we had. So, but what is interesting, if the Poisson ratio goes down, what is interesting is that when you look at the sound velocity of the system, and we start here at room temperature with the most porous system, it's about between 2,350 meters per second of a bulk system, and here you have 2,600. That means we have a porous system, which in principle has a smaller sound velocity, which has a higher sound velocity. And when we heat it step by step and around the glass transition temperature, where this becomes unstable, the sound velocity of our previously porous system and the bulk system coincides. So this is a direct measure of this porous structure. And we can also look at the scattering function of a total system. The only scattering function I want to show here is the scattering function of individual chains. And this is now a slide from Polymer people. What you see is, for the in-plane, we have a behavior which is roughly like a 2D self-avoiding walk. So when the chains go around the pores, that looks like that they arrange in a way as they were two-dimensional self-avoiding walks. I don't have a good theoretical argument for that, that this effective excluded volume works like this. And only when they are significantly larger than the diameter of the pores, then you get this Gaussian q to the minus 2 at very long scale, large length scales. It's a primitive path analysis. But you can add short chains, and one of the questions when we added short chains was, do they fill up the holes? But they don't fill up the holes. That's the interesting thing. They go into these bridges because there they have enough conformational freedom. On the surface of the holes, they would have a much smaller conformational phase space. And so they go into these bridges. The holes become a little bit larger because of the short chains. But as long as the whole system is kind of spanned by the long chains, they do not go to the holes and fill up the holes.
Isn't that the question of how many short chains you add?
Of course, if you add too many, that the effective entanglement length becomes too small, everything breaks together. That's clear. Of course, one can also think of completely the opposite situation, namely trying to make globules of very, very long chains, which are not entangled at all. And one way to do this is to take a chain of a good solvent and then collapse it very fast, and then we can make a melt of such globules out of that and see how they behave. And these systems stay rather stable like this. Again, one can make a very simple type of argument, which I think we first discussed together in the context of ring polymers. But I think more or less it's reasonable to argue like this. If you don't have a chain end here, for a loop coming out here into the other matrix of the other chain, you get the same problem of tube leakage type of behavior, which tries to prevent that. And there's also nice theoretical work by Tom McLeish and others which support this kind of picture. So what you find is these chains start to relax only by reeling out chain ends, and that takes very, very long. So these globules are stable for a very long time. And you can also make this, and that's why I'm showing that here, you can also do this experimentally. What you can do is you can use electrospinning. And if you take the right choice of solvent, in that case it was chloroform because it is very, very volatile. And concentration, you see that this very fine jet for concentration here in the solution, which is below the overlap concentration of the chains, this jet breaks into very many small droplets, and what you have here are little spheres of particles. And when you analyze the spheres of particles, you see typically that one sphere here only has one chain. So there's a little sphere with one very long polymer chain, and this polymer chain is collapsed extremely fast, but it didn't have a chance to entangle. And then we can do the same type of experiment and analysis and look, for instance, at the glass transition of these systems, and it looks like, at least from the simulation, that the glass transition of this system and this system is the same. Here there are some difficulties with the experiments concerning surface effects. We are still discussing that, but I think it's interesting, a nice system to look at. Well, this one can go on with and discuss in different contexts as well. You might know, of course, being here with people like Rosberg and many others, that in chromosomes we have a situation that the different in the interface cell nucleus, that the different chromosomes occupy well-separated territories, and that they are stable on the time scale which is needed to perform a biological function. And in principle, this system is very close to this system when it comes to these contexts from polymer physics or statistical physics. But to go into that would be another talk, and that would be too much. With this, I would like to thank you very much for your attention.
And the court. Yes, David.
So the method you described for making nanoporous films would lend itself to roll processing. You could have a roll, then a hot area to pull the nanopores into the film, and then a cold reel to take it up.
You need the biaxial pulling, then it should work. So we are actually now setting up. So we tried something which a theoretician typically doesn't do. We tried to find a patent. Okay. Yeah, because it's the first time that somebody produced a nanoporous film just from a dry polymer system. Otherwise, you always have solvent or chemistry which makes crosslinks and so on. And we actually in the process of having a test cycle with a special machine which can do this almost in technical scales and speeds. But it's a slow process. So polystyrene works very well. We tried the same with PMMA, which should be as good as polystyrene when you take entanglement length, molecular weight and everything. But when you take the Vogel-Fulcher behavior, PMMA is much steeper, and it would take, for the same chain length, roughly 100 times as much as polystyrene to produce the same results. That's where the chemistry catches up. No? We can avoid the chemistry as much as possible, but when it comes to the real system, it gets at you.
How can you make the dry polymer? So then you always have like some hydration shell, like can you completely get rid of
It's a standard melt. You can, with polystyrene you can buy. You can buy a 1 million molecular weight polystyrene with a very small, fine molecular weight. What was it? The index was 1.04 or
So it's
something
like a
like
powder?
this. Yeah, it's a
Yeah.
powder. Yeah. It's a powder, and then you can make a pellet
Yeah.
and a little plate, and then you can expand it.
So the pores that you showed were on the order of 100 nanometers.
We go of the order of typically 6 to 8, 10 tube diameters.
Okay, but the 100 nanometer number struck me because that is sort of like butterfly wings and things like, and beetle scales. So are these films, do they have structural color? Are they blue?
The ones I have are just
Clear.
clear.
But they must have some, like there does seem to be a characteristic pore size that would suggest that there would be characteristic bright scattering.
Question is do you need a rather narrow distribution of sizes, or
Butterflies work.
so if we get this if we get
It's either structure at the level of the relative positions of the holes, or it's about the dielectric contrast of the holes.
Well,
Right.
polystyrene has a really high dielectric contrast.
Yeah.
That's like 1.6, that's nuts.
so when this test run which we are planning for mid-December, there's a company which does this for industry, and we got a day to look at that. If you get about 100 samples or so of this size, then we can have a look. Maybe I'll give you one. Have a look at it.
So recipe-wise, are there magic numbers? Is it like, what, is there a minimum number of monomers for which you will have a particular separation between entanglements such that you will have enough to make these circles? Like, do you learn something about principles of design so that you can actually control, say,
So we did not systematically vary the chain length. However, when I take here the typical, this one is good. So when I take this situation here, so you see that these chains expand over many such holes. And taking this situation, I would expect that you need at least about a third of this chain length. And that would mean, in the case of polystyrene, somewhere between 300,000 and 400,000. So we are now trying to get some long-chain polycarbonate, which would have many advantages also from a technological point of view. But I learned that besides somewhere in a drawer from the 60s at Bayer, there is no long-chain polycarbonate available.
So this is all based on linear chains.
Yes.
What would happen if you made them either branch, so you could get this phenomena from just say one chain, or if you had things that can link up together post festum? So you start with linear chains, but then they can interact.
Okay, so so two questions. If you would have a branch chain with a few branches only,
Yeah.
I would not expect a dramatic difference.
Okay.
The point is when the branches are becoming so dense that in principle between here and here and here and here you would have many contacts. Now, then it would not allow to have these pores, to make these pores. And what was the second question?
The second one was, have you tried things that involve interactions along the chain or between chains that are specifically engineered?
No, that is only attractive in the way that the starting film is a stable, thick film, from a molecular point of view, thick film, which has a pressure zero, so to speak. So that is what you have in the experiment as well. And so far we have an attractive interaction between the beads. Of course, what one could do, but when one would really need a very careful, systematic study of the experiments, when you could take a block copolymer
Wait, you said attractive interaction between the beads, but not all of these are not attractive.
No, they're all attractive because otherwise,
This is not entropy based that they collapse. This is because they actually stick to each other.
no, the point is here. So when you start out here, this is an equilibrium film. So the pressure here is zero.
Okay.
And in order to have a pressure zero, you have to have a weak attraction. Otherwise, the polymers would fly away.
Got it.
And this is what you have. Now, what you are suggesting is something different. What one could do is, one could, for instance, think of a block copolymer in a way that you adjust the surface tension, and via the chains themselves, you define the size of the pores through the entanglement length, and with these little pieces in between, you could try to arrive at a surface coating.
Such that
Things like this one could try.
such that your principle of design would be to design the sequence of your diblock or your triblock such that you have holes of a given
Yes,
size.
but you have holes, and you have holes with a specific surface property.
Okay. Cool.
But that needs more chemistry than I can do.
I have actually a question which is related to Jason's question. You explained this philosophy of the difference between prefactors, which are chemistry dependent, and universal scaling physics-based properties. This tightening of knots, that is the basis of your holes and everything else, this seems to be, if initial state is dominated by physics scaling, then tightening of knots seems to be the more tightened the knot is, the more sensitive it is to local chemical details of the model.
Because there are two aspects to it. On the one hand, of course, the local chemistry determines the increase of bead friction from the tightening.
Yeah,
That's what you just mentioned.
Possibilities to.
Yes. So that is coming from the local chemistry. But also, if the bead friction is too small, it can pull in the ends probably eventually too fast. So you have this interplay, especially for this first part where you just elongate the system. If the bead friction is too small, then the chains can pull in too fast, or that means on the other hand we pull too slowly.
Okay, so are you saying that it sort of compensates one and the other compensate each other?
Yeah. So it's this game here, no?
Interesting.
It's this game here which one can play with.
I see. If anyone wants to know the history of how Dijon discovered n equals 0 theorem, I'm happy to tell. But otherwise, thank you very much for super
Thank you very much.
interesting.